Okay, so we are live. Apologies for the delay. Just a quick sound check. I know Sohan can hear me. What about the rest? Can you hear me and see the slides? Okay, cool. Thank you so much. Another Friday, and I'm really sorry for the delay. It's all due to the issues with the LaTeX server. We think it's to do with the AWS, but anyway, it doesn't matter. So sorry for that. Let me just maximize this. So yeah, you can all see. Do you see the slides after I did the maximum? I did maximize it. Okay, cool. Thank you. Okay, so let me just go through the stuff that we'll cover. So today I won't go through the recap of the previous session, not least because we are starting late. But essentially today's session will be split in two parts. Originally, I wasn't planning to do this, but I felt we needed to do a bit of recap on the group theory side, only things that we need in order to help you. So that's one of the reasons. So we'll start with the pre-lecture comments. I will be very brief, and then diving into part A, which will cover groups, in this case, multiplicative groups, rather than so the binary operations will assume it to be multiplication as opposed to working on an abstract binary operation just to cut the chase and go straight to the matrix group stuff. So it's more natural. And then we'll go through these other concepts, and then finally we will dive into part B, where we will focus on these things this week, and then next week we'll carry on from where we are left. Okay, so let me go. So this is where we are. So there's only one column left. Congratulations to all of you. I know most of you who are regular or attending at the moment alive. You've done very well. So very well done. Congratulations for being patient, go through the basics to get into where we are actually starting to get into the more of a quantum related stuff. Okay, so we are here today. We will mostly focus on the general linear group, and then next the special linear group, and then next week we will dive into the unitary group and the special unitary group. So that should set up the stage for us to, once we get into the Hilbert space section. Some of you might have noticed I've changed the title. It used to be complex Hilbert spaces, but I think by now you realize that we will only cover finite dimensional Hilbert spaces, so I might as well just stick it there. And then another thing some of you might have noticed is that I have added an extra lecture in this section. So the reason for that is because in here we want to focus on single systems. Okay, so no tensor products, all of that, this stuff to make it easier for you. And then in here we will then cover the composite system. So we'll deal with the tensor products. Okay, so that's the only changes I've made thus far. So I don't anticipate any more changes. Next week, I will comment more on the scheduling stuff because we don't have time today. Okay. Another thing I want to add is recently it came to my attention that YouTube changed the policy that will essentially enable Google, enable them to run ads on videos, even if the creators, in our case, we don't want to run ads in our lectures. It seems from what I gather, it seems that Google will be able to do it anyway. So if that happens, we are left with no option than pulling down the videos on YouTube. The reason for that is because we don't really want to, not because A, we don't want to make money with the advertising, B, there is no guarantee that we don't want a situation where there are like hateful, racist and all these conspiracy theory stuff ads running in our stuff. So, and there's no guarantee that Google has, their algorithms will be able to flag, those things to not run next to our stuff. So we're left with no other option. If Google implements this, we'll have to pull down the YouTube videos, but they will still be available on Crowdcast. So this is the only thing I want to add here. Let me just check the chat. Okay. Okay, yeah, I see Soham is already, okay, cool. Yeah, thank you, Soham, for clarifying the stuff on the chat. Okay. So this is what I wanted to comment. At the end, we can have a conversation on this, and yeah. But just to let you know, especially those watching on YouTube later. Okay, so let's go to part 1. This is really a kind of an extension of what the introduction that we done, in the second lecture of this foundation module. But that lecture wasn't really, it was more tailored to like abelian groups, additive groups. The reason for that is because we wanted you to, to get you into the concept of rings and fields, and vector spaces more in a more natural way. So we focus more on the additive groups, but there were some parts that we touched on the multiplicative groups, like the matrix groups that we briefly mentioned in that section. So this section will give you more clarity. There's more structure. There's more bone. Sorry, there is more meat into the bone, if you will. So, okay. So let's start with the first definition. Okay. So I will say a multiplicative group. Because I don't want to work with any binary operation. We'll just, use the times. The multiplication is a pair where G is a non-empty set, and the multiplication, the times, is a closed binary operation that satisfies these actions. Most of you attending this already seen this. This is essentially just the group actions, right? So there is an identity. The identity. Times any element is the same as that element times identity equals the element itself. So the identity doesn't change the element. And then you have the associativity, blah, blah, blah. And then another important thing is that there is a inverse. So any element on the group does have an inverse, A minus 1, such that the product of A with its inverse gives the identity. Okay. And then another thing is that a group is commutative or abelian. You will see me sometimes I will use commutative, sometimes I will use the term abelian if obviously A times B equals B times A. Okay, otherwise we call it non-commutative or non-abelian. Okay, so by the way, I was rushing to do the slides. If some of you notice any typos, apologies in advance. Let me know. Okay, so I assume there is no problem here with the definition of group. This is just the group axioms that a lot of you have already been seeing this for some time. Okay, let me go next. And here's a proposition. This is this proposition. This is something that came across in the first session. I'll leave this as an exercise for you. Is that the identity in a group is unique, and the inverse element is also unique. This is what makes groups special. This is so these two properties are intrinsic on groups. So anything that doesn't have this is not a group. Cannot be called a group. Okay, they might satisfy the associativity and all of that, but if the identity is not unique, if this thing is not a group, it fails to be a group. A group has to satisfy this. Okay. Now another convention, as some of you already, most of you watching this live session will know, instead of writing this, we'll just write AB to denote the product as opposed to writing this, just to save us. And now I'm going to define this C star. Don't mistake this with something that I've been mentioning, which is the C star algebra. This is something else, okay? But, I couldn't maybe put a multiplication sign there, but never mind. So this is a set of all complex numbers, non-zero complex numbers, okay? And the question is this a group under the multiplication in the complex number? Remember, complex numbers are a field. If yes, is it abelian or non-abelian? Does anyone want to have a go? Yeah, anybody on the chat? Okay, I will leave it to you on the chat to decide, but I will help you. For sure, this is a group. It's a group. And yeah, by the way, it's abelian also, because obviously C is abelian. C is a field. So C star indeed is a group. Okay, just take a note of this because we will use it later in the matrix group to do something. So just take note of this this set. Okay, it's a group also. Let me check the chat. Yes, Soham. Thank you, Soham. Okay, so another concept that we went through briefly in the previous group intro to groups is that of a subgroup. Okay, so we say a subset H is a subgroup if it is also a group under the same multiplication rule as G. Okay, so with this we can see that G is trivially a group itself, and the same with the identity element E. Okay. Now, here's a question that I won't help you, but this is very interesting, is whether you can find, well, I already told you, you already know that C star is a group. The question is, can you find other non-trivial subgroups of C star? I guarantee you there are, but can you find them? Go and scratch your head around and maybe, post on the Gitter if you find anything. Next week we can take it from there. Okay. And here's a proposition, which is, let's say this is the test case for, being a group, a subgroup. Okay. So H is a subgroup if and only if it such the following conditions hold, right? The identity is also in H. The product of any two elements is also in H, and if any element belongs to H, the inverse of that element also belongs to H. Okay, so I will leave this also. Looking at the group definitions, I believe you will be able to prove this. Or if you are having issues, go back to the reference group. Apologies. The study materials that we shared on groups. You should see proofs of all this. Okay. Let me just check the chat. Okay. Okay, so Nicholas, no, N. So I assume you mean N. So N being the natural numbers. So George is also stepping in. Is that what? So let's just break it down. So you mean N as the natural number if N star is a group? Remember what a group is, right? It has to be a closed binary. The operation, the multiplication has to be a binary operation, okay? So N, and also it has to, the group has to have, any element has to have an inverse. Of course, multiplication is closed in N, but where does N fails to be a group? Z, okay. But Z also fails to be a group because Z is a ring. It's a ring, but it's not a group because it fails on the inverse. Not every element in Z has an inverse, right? This is something that you can. Yeah. Okay. Cool. So it's just a matter of looking at the axioms for the thing, So just if you see a set, look at it and see, because for example here it says, so in the case of Z, you can easily test, pick an element of Z and see that looking at the characteristics of Z, I mean the way Z is, to see that not every element has a multiplicative inverse. Okay, so I assume that's okay. Another thing I didn't cover in the previous section on groups is this concept of a group homomorphism. So group homomorphisms is the analogous of linear maps, in the sense that group homomorphisms, they preserve the algebraic structure of a group, okay? So we say a map going from G1 to G2 is a homomorphism if f of AB is the same as f of A times f of B, okay, for all. Okay, this is very important, this notion of homomorphism. There is also a concept of homomorphism with the rings, ring homomorphism, and this is a very interesting thing. It has a lot of interesting applications in cryptography. Have you guys heard about homomorphic encryption? Well, as the name suggests, it's to do with this property. Okay, in a nutshell. So here's a question: if E1 and E2 are, the respective identities of G1 and G2, is it true that f of E1 equals f of E2? So in other words, do the homomorphisms, they take identity into identity? I think this is very obvious from this. I hope you can see this is true. Okay, and then another thing is that if F is a bijective map, so I forgot the word map here, so apologies for the typo. Then F is a group isomorphism, and we write this. So just like in the vector space case, we were writing vector space isomorphism. This is the analogous for group isomorphism. Okay, and then another thing is the concept of the image. Remember, in linear maps, we also define the image. So the image of F here, in this case, in the group sense, is the set of all elements in G2 that are, generated from elements of that are mapped from elements of G1. Okay, so this is also a very natural thing, because you already know, in linear maps, we didn't call it image, we call it range, but it's more or less the same thing. The only thing we are dealing with a different structure, okay? So the claim now is that is whether the image of F is a subgroup of G. What do you guys think? Yes or no? Is the image is this set a subgroup of G2? Not necessarily. Well, you will see that. I will let you think about it. If there is a bijection, then obviously yes, because then it will be the entire, the image will be the entire group G, and that's, G2. Then as it's obviously a group, then yes, but not necessarily. It doesn't have to be. Yes, it is a subgroup. Okay, I'll let you just go. It's very very hard to just come up with the thing on the fly. I know it's very hard for me to be asking this. Yeah, but take your time and go and rationalize about this and come up and find out under what circumstances this could be a group, and under what circumstances that F has to be bijective, and what does that mean? Okay, we'll come to that. Another important definition is that of kernel. So we've seen this in linear operators. Well, there is just a similar concept in the group sense. So the kernel of F is all the elements of G1 that are mapped into the identity of the second group, okay? Where E2 is the identity of G2. So the same question again is ker of F a subgroup of G1? Yes, it is a subgroup. Why is the identity not 0? So, okay, so it's not 0 because we are not talking about abelian additive groups, you know. So the 0 notation, remember, when we are talking about vector spaces, 0 notation is conveniently used, you know, just to make it natural, right? When we talk about vector spaces, that's why we use the additive notation for additive groups. But this is not an additive group, so the identity is not 0. I mean, you could call it also 0 instead of a thing, but it would be very weird. So we leave the 0 notation only for additive groups, not multiplicative. So when you use addition as a binary operation, you use 0 as identity. And when you use multiplication as a binary, concept of multiplication, not necessarily to do with normal multiplication. Anything that you call multiplication, you by convention, you don't use 0. Okay, this is just a notational stuff. And I understand this might be very a little bit confusing, but it's generally, as you get used to it, you become like, oh, it makes sense, you know. So I don't know if this answered the doubts of our friend Amir. Are you okay, Amir, with this? Mm-hmm. So it's not so much about labeling convention, he's saying. Yeah, but wait a minute. This is not, remember, we are talking about groups. We are not talking about vector spaces, huh? Okay. We are talking about groups. You know, vector spaces happen to be groups, but they are additive groups, right? You know, they have addition on them. But forget that for now. Now we are just talking about groups, not the vector space structure. Okay. It's very confusing because obviously this is the thing, because this is a thing of abstract algebra. There are a lot of things that are intertwined together, but you know, you have to be very contextual in what context these things are being used. So just block down vector spaces for now. Just focus on the thing on groups. Okay. Yeah, 0 can be, in the case of vector space, yes, 0 can be a trivial null space. Yes, it's true. But we are not talking about vector spaces. We are talking about groups. Okay. In this case, we are talking about multiplicative groups. So, you know, the notion of addition doesn't exist in here. Whether that, I hope that, I don't know if that helps with the abstraction. It's not easy. I know. Okay. This is the thing. What happened? This is the thing. The interplay between the different structures and these things in quantum mechanics. You know, this is why sometimes you see these online courses. You know, teaching introduction to quantum computing. Yeah, you do. It's all about matrices and all this and that and these things. But there are a lot of there are different fields of mathematics in the play. Really. So actually, the approach we have taken, I hope, has been deliberately done for you to be able to see, especially to separate the algebraic aspects of the theory from the other aspect that we will be getting on, like the geometric, the topological stuff. Okay. So far we've been just focusing on the algebraic aspect of the mathematical formalism, but gradually, especially in the advanced stuff where you know we deal with the functional analysis and measure theory, other branches of mathematics, it becomes more obvious. Okay, so let me go. So it is true, I can guarantee you, and you can see also this, if you go to the study materials on group theory, you will see that the kernel of F is a subgroup. Okay, now the question of whether it's abelian or non-abelian, I was saying here, I forgot to comment on this, will obviously depend on the underlying group. Okay, in fact, we'll get to something interesting once we get to matrix groups on that. Okay. Now, our friends again, the commutators. Who missed the commutators? Okay, so we define the notion. The reason I'm defining commutators, I want to use the definition of commutator to define something else. Okay, you will see in a minute what that is. So the group, the commutator between any two elements of the group is defined like this. So you multiply the multiplicative inverses of the two elements, and then you multiply the product of the two elements. So it's essentially like this. Okay, not essentially. This is how it is defined. Okay, and then here's a proposition. You might have, I believe in the first session, we have done this, but for the general linear group, when we defined it more or less in a sloppy way. Today we will define it properly. And, you know, these propositions here appear there. So, for example, I think this is the only thing that, this line is the only thing that didn't appear in that, in the other session. So, the claim is that G is abelian if and only if the commutator of any two elements equals to the identity. Okay, I think if you go and think about it, you don't need to, you know, convince yourself about this. You know, that's why I'll leave this as a home challenge for you. And actually, on that, this is where it's really important for you guys when you go in this gap before coming up to the next session, you know, to take your time to go through these things so you can internalize them. That's the only way that you will observe these things, and, you know, they become natural to you. Okay. So I'll leave this to you as homework. So one thing I want to comment is that, in a nutshell, the commutator is a measure. There's a typo here. I meant measure, not measures. My English teacher would have been like, okay. Anyway, so the commutator measures on how abelian a group is. Okay, and in fact, in most interesting practical applications in pure mathematics, or to an extent in physics, the less abelian the group is, the better. Okay. And then this brings a question, wouldn't it be nice to have a way, given a group, a non-abelian group, to have a way of you know, filtering out the non-abelian side of it, or I mean, sort of identify the parts of the groups that are abelian? Well, there is. And this brings us to the concept of the center of a group. Okay? So the center of a group is defined as this. So is the elements of the group that commutes with all the elements of G. So the commutator of so it's A. The commutator of the commutator of the elements of the center with any other elements of the group is the identity. Okay. Now, in most textbooks, this is how the center is defined. So this is the way you will probably see it if you look at the study materials and these things. You know, this is how you will see the center. The reason I did this is because you know, the two are equivalent. Really, for me, this is more static. This is more elegant to do it this way. And another reason is that you start getting used to the commutators, because, you know, in the advanced module, when we start talking about Lie groups and Lie algebras, it's very important that you start already thinking in terms of commutators. Okay, and it's also very important that you kind of differentiate the two types of commutators. This is the group commutator. There is the other commutator for rings, or more formally for algebras, that we will touch at some point later. But it's very important to kind of to not mistake the two things, because we are talking about different algebraic structures. You know, a ring or an algebra has two binary operations. Yeah, it's a ring. Okay. So whereas a group only has one binary operation. So the group commutator, in this case, normally it's trivial to define the commutator on abelian groups. So you do it in non-abelian groups. That's in practice, that's where they become useful. Okay, they become interesting. So in this, if you ever do any exercise, and this time using any software that, you know, probably written by physicists, be careful, because if you are computing something, you say, oh yeah, I'm going to compute the commutator of this and that. It might be the other commutator that I kind of call it like the Heisenberg style of commutator, but this is the group commutator. So be very, very aware of the two contest. This is where things have to be. You have to start thinking in contextual thing. if you are talking about groups, if a mathematician is talking to you about groups and he or she mentions a commutator, then you know it's a group commutator, okay? Not the ring, the algebra commutator, which we will touch at some point, okay? It means the center of the group is a subgroup of G. I believe you can also prove this, and I leave it as an exercise, okay? So in a nutshell, you will see this more in concrete when we get to the matrix group. The smaller the center, the less abelian the group is. By smaller, I mean the less elements, elements that the more limited this set is in terms of what sort of elements it has. The less abelian the group is. You will see this in a more concrete fashion when we get to the matrix group section. Okay, so I believe this is it. So now we are getting to the matrix group section, but let me pause here, just look at the chat and make sure we are all on the same page. Okay. At this point, does anyone have any questions, anything on this thing? Because the gear, we're going to switch on to something completely different, and then we'll come back again to group theoretic stuff. Yes. And you mentioned that the less abelian the group is, the better. Yes, it's more interesting because abelian groups are a little bit boring, right? So, yeah, the less the abelian, the better, really, because they give you all these exotic properties. That's in that sense. Okay. Does anyone else have any other question? Yes, the least abelian equals the same. Yeah. Yes, so thank you, George. That's true, yes. Oh, actually, let's see, least abelian. I'm trying to actually understand. No, if it's if it's abelian, then obviously, yeah. Just, I think I'm losing connection. It's buffering on my end. Sorry for that. If I lost you. Can you all hear me? Can you guys hear me? Ah, okay, yeah, thank you. The thing was loading. Yeah, so, okay, so Amir posted something. That's an interesting question, yeah. If the center equals, yeah. Sound was gone for a while back now. Yeah, sorry for that. It's like this thing is a bit of buffering, maybe my network. I will actually just reposition this because I moved a bit the router, so I'm not sure how it affects. So, but can you hear me? Yeah, okay, sorry for that. Okay, so there is no thing with this. This you will it's very hard to see the actual this kind of to see like an interesting picture of this in the abstract sense until we actually get to more concrete groups, which we will do now in the matrix group section. But before we go, as we move towards matrix groups, as I said, we'll focus on 2x2 matrices for this for a single system in this case, or for those who are coming from quantum computing, you can view every time that we do we are going to touch is relevant to single qubit systems. Okay, so that's why we're going to focus on this as a toy. This is also a way of enabling you for you to see what's going on, because you are able to do calculations, you are able to do stuff, see stuff if we stick with 2 by 2 matrices for most part. If we just jump straight to higher dimensions, like for n by n matrices, then it's very hard for you to see stuff. You'll see what I mean in a minute in some of the exercises that I will give you to do. Okay, so giving a matrix. Okay, so the determinant is defined like this. Okay, so essentially, you multiply this side of the diagonals times this other side. Sorry, you multiply this side, then you minus with this other side. Okay, so this is it. Okay, so you can see, hopefully I didn't make any mistake. If I do, apologies. The determinant of this, you can, it's straight, and this is actually very interesting because the determinant of the identity is 1. You will see this is actually very interesting for matrices with determinant 1. You will see why. And so a question I will ask you, you don't have to answer now, is to what about the other matrices such as the Y or H gate, for instance, for those of you coming from quantum computing stuff. Go and think about it. In fact, in a few slides time, I'll have some kind of encourage you to do something. I will share with you later. Okay, so the concept of determinant can also obviously be defined for any n. Okay. It can be defined for any end. In fact, we might do that, but in a more inductive way or recursive, as those of you coming from computer sciences will say. But for now, for the time being, we'll just focus on 2 by 2, as I was just mentioning. However, this is because this is easy to see. Interestingly, the diagonal for diagonal matrices, the determinant of it is just the multiplication of the diagonal elements. Okay, so. Let me just check the chat. Okay. Now, here are some interesting properties. As I said, I have a lot of hands-on challenge for you. So given 2 matrices and a lambda, a complex number lambda, the claim is that these identities hold. So the determinant of the transpose, you remember the transpose? This is one of the things that, starting from now, we will start bringing all the stuff that you've been learning, that we've been learning them like a kind of loosely together, to glue them together, okay? So it's like, we have like a plane, with all the fuselage, the wings, everything like scattered. Now we're going to put everything together, okay? So it's very important that you remember. You go back to stuff. If you don't remember what they mean, go back to the previous sessions and refresh yourselves. So in this case, so the determinant of the transpose is the same as the determinant of A. And another thing is that on the determinant of lambda times A equals lambda square times the determinant of A. So it's not maybe common sense, like intuition would just say, okay, maybe a determinant of lambda times A is equals to lambda times determinant of A. But that's not the case, okay? In fact, for n by n matrices, the determinant of lambda times A equals lambda to the n times the determinant of A. This is a very interesting property, right? And another important thing here worth mentioning is that the determinant of AB is the same as determinant of A times determinant of B. This is very interesting also, okay? And here's a proposition for you that if A is invertible, remember what invertibility means. We'll give you a theorem that actually helps you determine this. Then the inverse, then the determinant of the inverse equals 1 divided by the determinant of A. This is very interesting also, right? And here's obviously the definition of, when a matrix is invertible, if obviously there exists an inverse element. Notice I'm using the same notation as I was using in the abstract sense. This is deliberate, okay? So you can start seeing things, okay? So far, this is not a group. this thing is not a group yet. We're just viewing it as a set. It has a multiplication in these things, but parts of it will become a group. You will see in a minute, okay? Let me just check. Yeah. Okay. This is not a problem also. Now, this is a very important, that's why I called this theorem, because it's a very important result. It's a very important thing, is this, that given a matrix, in this case, we are doing two by two matrices, then the following statements are equivalent. By that, remember, when we say statements are equivalent, we mean that by proving one, you immediately prove the other. You only need to prove one of them. So in this case, it says the determinant of A is non-zero, A is invertible, and so on. Okay, so this means if I hand you a matrix and ask you, is a matrix A, and ask you, is A invertible? You know, you have all these choices to try to find the answers. Okay, so you could compute the determinant and see that the result is non-zero and say yes, is invertible because the determinant is non-zero. Okay. Likewise, if the determinant is zero, you can just say, you will say yes. No, it's not invertible because the determinant is zero. Okay, so any of these you can choose whichever is convenient for you. This one also, this might be very very convenient for you if the rows of A are linearly independent. So if you view, in that case, you would have to view this as this is a bit confusing in a way, because you have to bring in vector space structure and these things. I don't know even why I added it, because this just adds into the confusion. But anyway, if you look at the rows of the matrix, if they are linearly independent, you know, remember what linear independency means. You can immediately, this is essentially a hack. You can say safely that A is invertible. You know, to help you see this, let's go through the thing. Look at the identity, for example. You see. So in C2, so look at this as a vector in C2. So these two, so this will be like, you know, what qubit would this be, you know? So you look at this is the row, the first row, and this is the second row. These vectors are linearly independent if you view them as elements of C2, for example, okay? So I know it's a bit confusing. I actually don't know why I included it, because we are talking about groups, and now I'm telling you about linearly independent stuff to do with the vector spaces. But yeah, it's just to help you. But anyway, you can do the invertibility stuff simply by checking the determinant of it. You know, it's very easy to compute the determinant in this case for 2 by 2 matrices. You just look at the formula and compute it and say, yeah, it's invertible because the determinant is non-zero. Otherwise, it's non-invertible. Okay. Let me check the chat. Okay. Okay, thank you, Soham, for keeping up on the chat. Now, this is obviously, this is to check. This helps you check whether a matrix is invertible or not, but it doesn't tell you what's the inverse of the matrix, right? So the question is there a way to compute the inverse of matrix using determinant? And the answer is yes, there is. So this is why the determinants are very important. Not just they tell you whether a matrix is invertible, but also it gives you a way of computing its inverse, okay? So here's a formula. I hope I didn't make any typo. If I did, apologies. So given a matrix, this is how you find the inverse of it. Okay, you can do this. It's just you know, computational stuff. You just do the computation or manual or whatever. You'll be able. So in general, actually, for n by n matrix, you know, if the matrix is invertible, then its inverse can be found like this, where this thing here is the classical adjoint of the matrix. I won't touch this the time because we are not. This is not something that we will deal with. But you can check this in the books. In the thing, you will see the adjoint. This is the adjoint, the matrix adjoint of A. So this is for any matrix. This is how you compute its inverse. So therefore, this matrix here, this is the adjoint of A. Okay. So a challenge I'm going to ask you, I know it's a bit trivial, is actually to use this formula to do with the, those of you in quantum computing, you've probably done this just to and verify that the formula is correct. For these guys, you will see, you already know the answer for the inverse, what the inverse of these guys are. You know what the answer, because obviously they are unitary. Even in fact, we don't know yet because we haven't touched what unitary matrix means. But yeah. For the rest, I would definitely encourage you to just look at these and do this. Okay. Now, the important thing is the general linear group. We are getting almost close to the end of session. So then we can define the general linear group. Remember, the way we defined it last time was that is the set of all invertible matrices. Okay, but now today we found out that being invertible matrix is the same as having non-zero determinant. Okay, so we can redefine the general linear group in this term, and this will be very useful, as you will see. Okay, so it's a set of all matrices in 2x2 matrices in this case, because we are using 2x2 matrices that have determinant non-zero. Okay, this can also be generalized. Okay. To any n, okay? So it's the same definition, okay? In fact, the general linear group of, it's called general linear group of order 2, or if for any n, you call it general linear group of order n, okay? And this is actually very interesting, is that this is just side note. You don't need to even take a note or whatever, maybe for those studying physics and these things, you can go and, find about this. But we'll cover Lie groups and Lie algebras in the advanced module. But it's a prototype, but this is an example of a Lie group, which means it's a group that's a topological manifold. It comes also with a topological structure, okay? So this is a very interesting thing. But in practice, in fact, I have some comments to make here. I forgot. So this is just to recap that the general linear group being group, obviously the theorem is saying that it's a group. Okay. So, sorry. So to be a group, obviously, it has to satisfy all this. This is just, I've just added this to help you, especially those of you who are not that comfortable with stuff, So it means this, okay? GLN, the proposition claiming that it's a group implies this, that it GL of 2, sorry, not GLN, GL of 2 satisfies this. In fact, it told GLN of for any n also satisfies these things, this property, because it's the same. We are just working with n equals 2, but it can be generalized. Okay. Now, this is very interesting for those of you interested in quantum computing, because you probably, I will claim, you want n to be 2 to the k. Okay, so general linear group is very interesting for the thing, but for practical purposes, you only want some certain n's. Okay, even in mathematics, there are some occasions where n has to be of certain property and these things. In general, especially when you take into account, when the field has a non-zero characteristic, for example. Okay, so. Anyway, in quantum computing, you want n to be 2 to the k, where k is the number of qubits that you are studying or whatever you are interested in. Okay, because that way the elements of this, which then act on the vector space, which you will see in a few sessions time. This is a Hilbert space, so that way you have that. So n in quantum computing, you want not any n, but you want an n that's 2 to the k of where a k is the number of qubit. Okay, this is just a quantum hint. Remember when we started, I said we will have like these hints in order to help you. Well, there's one. This is very important, and this is just a curiosity stuff. You don't have to worry about this, but you have to be careful. There are some things that even take into account whether n is even or odd. So so not everything. I will try to, so there are certain things, whenever something that works with n equals 2 is true, I will tell you, Things that are not true, I will not tell you because there are things. So anything that I have to tell you, it also works for any n. I'll tell you. Okay. Here's the center. So in fact, I will go back. Yes, okay. So here's a proposition for you as a home challenge. So the proposition is that the center of the general linear group of order 2 is of this form, okay? Where lambda, this is the reason why I was asking you to take note of C star. Remember, C star is a non-zero, is the set of all non-zero complex numbers, okay? So this means that the center of the general linear group has this form, okay? So you can see this center is a very small, right? Because these matrices is just like diagonal matrices, right? So this means that is a, if you will, remember I was saying that the center measures how non-abelian, how abelian a group is. So this means that the general linear group is very non-abelian, right? Because the center is only made of matrices of this form, okay? In fact, you can generalize this to n. This is also true, that the center of a general linear group of order n, its element has this form where In is the matrix identity, okay, which has ones all over the diagonal entries. Okay, so I hope you found this interesting. So, and this will take me to the next session, which is the next thing. This is the end of the session, this part. The special linear group, which is defined as a subset of the general linear group, but whose elements yield the determinant of its elements is 1. So the set of all matrices in GL that have determinant 1. Okay, this can also, is true that this can also be generalized to any n. Okay, and the claim then is, in this proposition 1.5, is that SL2 is a subgroup of GL2. Okay, so this is called the special linear group. Okay, by the way, if you notice this kind of inconsistency on the definition, the numbering, and the proposition, is because I've been rushing and these things, let me know so I can correct them. But yeah, so this is a subgroup. Okay, remember what a subgroup means. You go to the definition in the group section in the slides. This will be later available, and you will be able to prove this, that this is a subgroup. Okay, this can also be generalized to this. Now, the interesting question, I don't want you to answer now. Go and think about it, because it's not easy. It might take a little bit thinking. What could be the center of this group? Or more generally, the center of this. But forget this. This is too general for any n. Just let's stick with n equals 2. What could be the center of this? I'll leave this as a thing. I will come back to it in the next session. Okay, but go and think about it. What could the center of this be? Okay, and another thing, especially those guys interested in quantum computing or already doing it, I know a lot of you, is as a home challenge, try, identify all the single qubit gates, the ones that, have determinant 1. So if they have determinant 1, it means they belong to this group. And then try to apply them to the qubits on the Bloch sphere or whatever, and see what happens. Just as a thing, because this is the thing. By doing this, you are actually seeing, how the abstract stuff is working on a concrete stuff. Okay, so I really encourage you. This is where you can actually go and play around with the thing. Identify all these gates. I know we haven't defined unitary operators yet, but I can guarantee you the quantum gates. The ones with the determinant 1 at least are elements of this. So you can, as a home challenge, I challenge you. I really encourage you to go that. Okay. Okay. Yes. So Soham partly. Yes, Soham. Though I will leave it for the others also. That's the thing. Maybe even on the Gitter, if you can paste that, because then the mathematical typesetting is much more thing for them to see. Thank you again. Okay, so the other section, the other thing I want to think is, what if you view the determinant as a homomorphism? It is a homomorphism, right? Because the determinant of determinant goes from GL2 to C star, and we know C star is a group, right? In other words, the determinant satisfies this, and this is already trivial because you already proved this, right? Because it's part of this. What is it? I'm going back again. It's part of this here. So if you already proved this, you will be able to prove that the determinant is indeed a homomorphism from GL2 to C star. This is very interesting, right? And now the question to ask is, what could the kernel of the determinant be? What's the kernel of this homomorphism? Yes, SL. Yes, well done, Nicholas. It's true. Yes, 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 yes. So as you can see, there you go. So the determinant is very interesting concept, really. Not just enables you with the it helps you, but it also helps you extract so many interesting properties about these groups. Okay, so yeah, well done for that. And the true also, it satisfies for any n. This is also true. Okay, so we leave it here for today. Well done to all of you. Thank you for the patience. Before I comment, I will just say, next week we will go through, carry on from here. We'll go cover the unitary group and then the special unitary group. But it won't be the end of groups because they will show up again as we go along, but at least you will have a solid foundation. So I really encourage you to go back to the slides again and, do the exercises, so you can get these things into your head, because we are getting really into the quantum stuff. If you get lost into this, it will be very hard for you, okay? Now, let me go back. In terms of the study materials, this is the provisional thing I found from Denis Serre. It's a very interesting book, but it might be very hard to read at some point because this is a kind of a graduate textbook in mathematics, but I trust you will be able to read this. So give me feedback on how hard it is. If it's too hard, then maybe I'll find something else for you guys. So, chapter for you to focus is like, the chapter 2, what are matrices, chapter 3, square matrices. So combined together, they go from pages 15 to pages 38. Now, another thing is, I have a copy of this, but I'm not sure if I'm allowed. I don't think I'm allowed to upload it to the GitHub repo and these things. But you can Google this. There is you will find a PDF version of this. But I'm also happy to email you a URL for you to think, because we don't want to put it on GitHub repo for us to get a takedown notice because of the licensing. But yeah, so I really encourage you. This is a little bit harder to read because it's a little bit. This is essentially this is a handbook for mathematicians. But I believe your mindset is already prepared. I would say have enough in terms of feeling comfortable with abstraction a little bit for you to be able to start reading these harder mathematical textbooks. So, but I will just say give me feedback on the thing. I will actually maybe next week I will run a poll whether you want to continue with this or I should find another textbook that's much more digestible. Okay, and as you can see, is actually the last name. You can see is I think he's if I'm not mistaken, he's a nephew of Jean-Pierre Serre from Bourbaki, Some of you being watching the newsletters, you know. So yeah, but anyway, give me feedback about whether it's too hard. Maybe I can find something else. But this is, let's say this is a provisional for this section, whatever to do with groups, and also in essence a bit of the quantum operators also, though I might add some supplementary stuff to that, you know, especially when we're dealing with the diagonalization and these things. This already covers a lot of stuff to do with matrices, okay, that we will cover in the quantum operator section. So there might be another companion of it, yeah. But the first is, let me know, give me your feedback next time to see whether this is too hard, you want something easier to read, then yeah, okay. Finally, this will be available on YouTube, and I will upload this slide. And I will email you the link to for those of you who want to download stuff, or you can go and Google and find it, the book, the study material book. And just bear in mind about the YouTube stuff that I mentioned at the beginning. At the moment, we haven't seen any ads as in our videos as far as we know. But if that starts happening, we have to pull down, because we don't want a situation where, you know, we have all this conspiracy theory, racism, and all this type of ads running in our stuff. Okay, so we have no option, but the lectures will be available on Crowdcast, and maybe we'll find another way, maybe host it in somewhere else. So yeah, maybe this is a thing. Maybe some of you, the developers on the audience, maybe you should create a YouTube for science or something, you know, with no ads and these things. You know, find a business model that can sustain you without getting into the ad stuff. You know, to host quantum technical talks and these things. So yeah, just a suggestion for the developers. Maybe you can do this. So that's it. I don't know if anybody have any comments, not just about the stuff. Let me go back again. Or in any general commentary. Next week I'll comment more on the schedule for the next few Christmas period and January. Okay. If nobody has a question, then yeah, thank you, Amir. Glad you enjoyed it. If nobody has, then we catch up next Friday. And oh, by the way, obviously today I started late by accident. You know, if most of you still feel comfortable with this, next week we can do the same. But it's not a thing. We can still start. As usual. I will make sure that I will do the slides in advance, not lastminute.com. But yeah, let me know. Soham, you want to add any comments? Is there anything that I might have missed in the chat, because I haven't been paying attention, I mean. Okay.
No, I think you answered pretty much everything. Yeah, but maybe it will be good to keep the original time from next.
Okay, we will keep the same time then, because Amir is saying, yeah, that's fine. This is the thing, because you guys attending the live sessions, I would rather tailor it to you so you can attend than those who are watching on the thing. So yeah, so we'll keep the same, and I'll make sure that next time there won't be any delays. Okay, so apologies for that. It's just these unforeseen things with the cloud stuff.
Yeah.
Okay, so good. So well, have a good weekend, and I'll see you all next week. Thank you again, Soham, for the help on the chat. So yeah, we are really getting into the quantum stuff. So yeah, I'll see you next time.
Thank you.
Okay.